Topic 17 focuses on intermolecular forces. These are the forces of attraction that exist between one molecule and its neighbour. The term also applies to the attractive forces between a molecule and an ion, as well as the attractive forces between atoms of a group 18 element. First, we recap chemical bonding. These are called intramolecular forces as they occur within a substance. For example, they are responsible for holding the atoms of a molecule together. We will see how an uneven distribution of electrons within a molecule results in a polar molecule. This is our starting point to look at the 4 different types of intermolecular forces. But first, have you ever thought what is in the bubbles formed in boiling water? Could there be nothing in the bubbles? Or perhaps they contain a 2-to-1 mixture of hydrogen and oxygen gases? It is neither of these. The bubbles contain water vapour, that is gaseous H2O. A gas is very much less dense than a liquid, so the bubbles rise rapidly to the surface. In boiling water, we are seeing the change from a liquid to a gas. This is called a phase change. In boiling water, we put in energy, which overcomes the forces of attraction between one water molecule and its neighbour, the intermolecular forces, while all the time the chemical bonds hold the 2 hydrogen atoms to the oxygen atom within an individual water molecule. The boiling point of a substance is directly related to the attraction between the molecules of that substance. We have looked at 3 models for chemical bonding. Ionic bonding, in which one or more electrons are transferred from one type of atom to another type to form cations and anions, and the electrostatic attraction of oppositely charged ions results in a rigid lattice. This is the case for a substance such as sodium chloride. The second type of bonding is where electrons are shared between adjacent atoms in such a way to form a complete outer electron shell for each atom. This is called covalent bonding, and it's what holds together the atoms of all molecules. The final type of bonding we touched upon was metallic bonding, in which metal cations are held together by a mobile sea of electrons. Let's start by looking at covalent bonding within a molecule. If identical atoms are bonded together, such as in chlorine, Cl2, the electrons of the bond are equally shared between the 2 Cl atoms. If, however, 2 different atoms are covalently bonded, the electrons are unevenly shared between those atoms, with a greater share being closer to the more electronegative atom. This is the case in hydrogen chloride and results in the Cl end of the bond being relatively negative compared to the hydrogen end of the bond. Overall, the molecule remains uncharged, and this charge separation is very small compared to the charge on an ion. However, it results in what we call a polar bond, and in this case, we say the molecule is polar and has a dipole. Not all molecules that contain polar bonds possess a dipole. The geometry of the molecule is important. So in carbon dioxide, the symmetric distribution of the atoms means that this slightly negative oxygen on one side of the molecule is exactly balanced by the slightly negative oxygen on the other side of the molecule, with the result that CO2 has no dipole. The situation is different in a water molecule. Each HO bond is polar, and the overall angular shape of the molecule means that the polar bonds do not exactly balance, and so the molecule as a whole is polar and has a permanent dipole. The first intermolecular force we look at is between an ion and a molecule with a permanent dipole. This is called an ion dipole force, and for example, they are responsible for sodium chloride dissolving in water. The oxygen part of H2O is negative relative to the part of the molecule containing the bonded hydrogen atoms. The negative oxygen end of the dipole is attracted to the sodium cations of the ionic solid, and the relatively positive hydrogen end of the dipole is attracted to the chloride anions. While the energy of attraction between a single water molecule and an ion is much smaller than that between a cation and an anion, if many water molecules are involved, the sum of the ion dipole attractions can overcome the force of attraction holding the ions into a lattice, and the ions break away from the lattice and enter the solution surrounded by a sheath of water molecules. Some ionic solids are insoluble. Calcium carbonate, for example. Here, the attraction between the calcium cations and the carbonate anions is stronger than the ion dipole forces, and consequently, the solid does not dissolve in water. The next intermolecular force I want to look at exists between molecules that have a permanent dipole. In liquid hydrogen chloride, one can imagine the relatively slightly negative Cl end of the molecule being loosely associated with the relatively slightly positive H end of the neighbouring molecule. This holds together the molecules in the liquid a little more tightly than one would predict for a similar sized molecule with no permanent dipole. The evidence for this comes from the boiling point, which is related to the energy needed to separate each molecule from its neighbour when a compound undergoes a phase change from gas to liquid. The two molecules, HCl and SiH4, look very different, but they contain the same number of electrons. And as it is the electrons that occupy most of the space of an atom, we assume the molecules are approximately the same size. Hydrogen chloride has a permanent dipole, and dipole-dipole forces exist within liquid HCl. Silicon hydride, however, is a symmetric molecule and has no permanent dipole, and so dipole-dipole forces are not present. It is easier to separate one SiH4 molecule from its neighbour, and so it takes less energy to convert liquid SiH4 to gas, and the boiling point of SiH4 is lower than that of HCl. Data shows there is approximately a 20-degree difference in boiling points of the two substances, which is a direct result of the dipole-dipole forces present in HCl. Turning to the more complicated case of a mixture of two substances, one of which has a permanent dipole and the other does not, hydrogen chloride and bromine, for example. The molecules are in constant motion, and as a hydrogen chloride molecule approaches close to a bromine molecule, the permanent dipole of the HCl polarizes the electron distribution in the Br2 molecule, causing an induced dipole, and hence a slight attraction between the different molecules. An instant later, molecular motion may cause the molecules to separate, and the Br2 loses this polarity. But what holds together the molecules of a non-polar substance where no permanent dipole exists? A more sophisticated model of the electrons in a molecule visualizes them not as points of negative charge, but as a cloud of charge. The electron cloud of a molecule may fluctuate, and for an instant this creates a very small dipole moment in the molecule. A moment later, the fluctuation changes and the instantaneous dipole disappears. Any dipole in a molecule, however temporary, can induce a dipole in an adjacent molecule, resulting in a slight attraction between the molecules. These are instantaneous dipole-induced dipole attractions and are forming, disappearing, and reforming constantly in all liquids. These are called dispersion forces for short. Dispersion forces are always present, as they result from the polarization of an electron cloud. The greater the number of electrons present in a molecule, the stronger the dispersion forces. They also exist between atoms of the group 18 elements and explain the trend in boiling points. All group 18 elements are gases at room temperature, but they don't all have the same boiling point. Going down group 18 from helium to neon to argon to krypton to xenon and then to radon, the number of electrons in each atom increases. Consequently, the dispersion forces between the atoms increase down the group, and hence the boiling point increases down the group. Dispersion forces are present between all molecules, as well as the atoms of group 18 elements. They readily explain the boiling point trends between similar substances. For example, look at the group 14 hydrides. They all have a similar formula, CH4, SiH4, GeH4, and SnH4, and a similar geometry. These molecules are tetrahedral in shape and symmetric and have no permanent dipole. Going down the group 14 hydrides, the number of electrons on the central atom increases, and hence the number of electrons in the molecule as a whole increases. This results in increased dispersion forces and a higher boiling point. Now add the group 17 hydrides to our graph. These molecules have a permanent dipole and experience dipole-dipole forces as well as dispersion forces between the molecules. Consequently, all show a higher boiling point than the group 14 hydride of the same period. We also see an increase in boiling point going from HCl to HBr to HI, and this is a result of increased dispersion forces between the molecules. But what about HF, which is an outlier on our graph? HF molecules within the liquid are held together by dispersion forces, dipole-dipole forces, and another type of intermolecular force called a hydrogen bond. The hydrogen bonding present means HF has a much higher boiling point than expected for a molecule of its size. Hydrogen bonds were introduced in topic 13. They are a type of dipole-dipole force and only exists between a hydrogen bonded to a very electronegative atom, nitrogen, oxygen, or fluorine, and another atom of nitrogen, oxygen, or fluorine. Water shows extensive hydrogen bonding and consequently has a very high boiling point for a molecule of its small size. In the diagram, the hydrogen bond is represented by a dotted line between the OH of one water molecule and the oxygen of an adjacent water molecule. Note that hydrogen bonding is still weak compared to a covalent bond. The hydrogen bond in water is around 10% of the energy of the OH chemical bond in water. In summary, topic 17 examines the main forces that exist between molecules. These forces play a major role in dissolving an ionic substance in a polar liquid such as water. The boiling point of a liquid is directly related to how hard it is to separate one molecule from its neighbour in going from a liquid to a gas. A knowledge of the geometry of a molecule allows us to predict whether it has a dipole or not, and informs our understanding of the intermolecular forces between the molecules.